4.7 for something called the Hopitals Rule. So the Hopitals Rule is a way of sometimes, let's just say it like this. We're going to get a new tool for evaluating limits. It's not always applicable, and even if it's applicable, it may not be the best way to do something. However, I think you're going to agree that it makes a lot of the traditional limit problems a lot easier. Okay? So, this guy's one of my heroes. Let's get his name right. It's Hopitals. Right? So it's not Hopitals or whatever I've heard people say, or hospital or whatever. Okay? It's Hopitals. All right? When does the Hopitals Rule apply? Well, we've used this vocabulary before, but I just want to refresh it. The Hopitals Rule applies for certain types of indeterminate forms. Okay? So as a reminder, this expression right here, natural log of x over x minus 1, when we examine this as the limit as x approaches 1, has an indeterminate form 0 over 0. And the big issue was because of this x minus 1 in the denominator, we couldn't use our nice limit properties to break it up into little pieces and then eventually do direct substitution. Okay? Now, what often happened with these problems in the beginning of limits? Often we did some algebra to cause this denominator factor right here that's preventing us from doing direct substitution. We did some algebra to cancel it out. Of course, you can't do much algebra to get an x minus 1 to cancel out there. Okay? Maybe you could do it with algebra, I don't know, but you'd have to get pretty creative with your log properties if you're going to try to find a way to do it algebraically. Okay? Nonetheless, it has a limit, it has an interesting limit, and we're going to explore it. Okay? So, specifically, this had indeterminate form 0 over 0. Okay? So as a reminder, there are lots of indeterminate forms. First of all, indeterminate forms are never something that you can write. Okay? I wrote out 0 divided by 0 to describe the structure of the problem. You may never write in the middle of doing math work 0 divided by 0. Okay? It is only a way of classifying the type of problem that we're dealing with. Okay? There are lots of other indeterminate forms, such as plus minus infinity over plus minus infinity, infinity minus infinity, 0 times infinity, 0 to the 0th, infinity to the 0th, or 1 to the infinity. Those are all indeterminate forms. Okay? Essentially, when you have a limit problem that has one of those indeterminate forms, it's anybody's guess as to what that limit's going to come out to be. Sometimes it might approach 7, sometimes it might approach 0, sometimes it might approach infinity. It just depends on the structure of the problem. So there is no shortcutting that. Okay? Of course, it always broke my heart early on in this class when people would say, oh, let me plug in a 1 over 1, that gives me 0 over 0, and then they wrote it equal whatever. Whatever they wrote it equal, they were wrong. Okay? Yeah?
I was just seeing the 0 over 0. I remember on one of the homeworks, I think it might have been for one of the, I forgot which subject, but it was asking for what the value of x to the power of x would be if you plugged in 0. And the correct answer, I believe, was 1 when it gave it, but wouldn't that just be the exact form there?
So it may be that that we could explore the limit as x approaches 0 of x to the x. And it may be that that's 1. I don't know. We'd have to look at it. Okay? But if it is, that doesn't mean you can apply that rule to other problems of the same form. That's what indeterminate forms are saying. Just because it had this indeterminate form today and it came out this way, doesn't mean when it has the same indeterminate form, it will come out the same way. I don't recall that exact problem, so it'd be interesting to think about. But what you can't do is just plug in a 0 and plug in a 0 there, and say it's going to be whatever I think it should be. You have to explore it through limits because it is an indeterminate form. Okay. Great. So there is one other expression that you might think is an indeterminate form, but it's actually not. Okay? Don't really worry about that. If you think it's an indeterminate form, work with it as if it were, but you'll actually find out that it does evaluate to be 0, always. So you could just go ahead and shortcut that. Okay, so we have all of these indeterminate forms. LHospitals Rule, this is really important. LHospitals Rule only applies to these first two indeterminate forms. Those are the only two indeterminate forms with which you can immediately apply LHospitals Rule. We will learn how to apply LHospitals Rule for all the other indeterminate forms, but it will involve some algebraic rearranging of the problem before you can do so to put it into one of these two forms. How are we doing? It's really abstract so far. Okay, so here it is, LHospitals Rule. Okay, it is a huge time saver, and in some cases the only way we can do some of these problems. Okay, so suppose f and g are differentiable with the derivative of the denominator not equal to 0. Okay, then if the limit as x approaches a has the indeterminate form of one of the two types that I just mentioned, 0 over 0 or plus minus infinity over plus minus infinity. By the way, going forward, I'm just going to say infinity over infinity, but it could be any combination of pluses and minuses. Okay? Then the limit, so this limit here that I can't evaluate, because it has indeterminate form 0 over 0, I can't evaluate right away, will be the same as this limit here. The limit of the derivative of the numerator over the derivative of the denominator. Be careful here, folks. Here we're going to be really careful. Hopefully by now everyone has learned their quotient rule. And when you apply the quotient rule, you do not just take the derivative of the numerator over the derivative of the denominator. Hopefully everyone's learned that and gotten in trouble a couple times because everyone steps in it the first time out. Okay? But this is not saying do a quotient rule. This is just saying take the derivative of the numerator over the derivative of the denominator. Now that might help us. That might give us enough of a jump on the problem to be able to evaluate the limit. It might also not help us. Okay? So Hopitals Rule is a pretty powerful tool. It's not the end-all, beat-all tool for limits. Okay? All right, so let me show you one thing I want to make sure you do. Whenever you apply the Hopitals Rule, I want you to show me that you're applying it. Okay? You don't have to write out a whole lot of words. This is what I want you to do. Just put a little LH over the equal sign when you apply the Hopitals Rule. So I know what you just did. Okay? All right, so let's see. Here's an example of the Hopitals Rule in action. Here I've got this limit problem. What's its indeterminate form? Its indeterminate form is 0 over 0. Okay? I would recommend that you identify the indeterminate form. Now, folks, never did I write this equals 0 over 0. Does everyone notice that? I am never writing something equals 0 over 0. I am just simply giving you the structure of the problem. Okay, what did I do from here to here? Well, it looks like all I did was cancel out an x, and I can follow you on that, right? And notice that it still has indeterminate form 0 over 0. Okay, what did I do from here to here? Well, my dear reader, I told you that I applied LHospitals Rule. Right? What is LHospitals? Well, first of all, can I apply LHospitals Rule? Well, yes. It has the indeterminate form 0 over 0, and both of these functions are differentiable. So we take the derivative of the numerator. What's the derivative of x squared minus x? It's 2x minus 1. Over the derivative of the denominator, which is 1. Now that's a legal move. Did it help us? Oh, yes. This no longer has an indeterminate form. Okay? This is not an IF, and in fact, we can use direct substitution on the second limit. So let's actually apply direct substitution to this, and we evaluate the limit. Now, is that the only way you could have done this problem? No. This is simply well, yeah, so we could have multiplied, say, by 1 over x squared to both the numerator and the denominator, simplified, and then we would have gotten there. Okay, so there's lots of ways we could have done this problem. Okay, but we chose to use the Hopitals Rule, and it was kind of slick because we never had to do any complicated algebra. Now, I'm not saying with the Hopitals Rule you'll never have to do algebra, but this was a huge time saver. Are there any questions on that? What do you guys think? So, usually on this exam I put 4 limit questions. Okay? One straightforward, the Hopitals Rule, one you have to do a couple of times, and then one grab bag, some other indeterminate form, and you won't know which one it's going to be. Okay? And then the 4th one will be a red herring, where the Hopitals Rule does not apply. Okay? Because I need to know that you know that you're checking to make sure you can actually use this rule. So be careful. So in this series of examples here, the Hopitals Rule will apply to most of them, but some of them it won't. Okay? Yeah.
Is that because the indeterminate form doesn't follow one of those 2 forms?
Well, or it might not be an indeterminate form at all. Okay? And it's very common for folks to just, like in this section, you'll just start taking the derivative of the numerator over the derivative of the denominator. You could always do that, provided your numerator and denominator were differentiable. You could always do that, but whether it's allowed depends on whether it had this correct indeterminate form to begin with. When it's a different indeterminate form, you can usually rearrange it. We'll see how to do that here. Yeah. So let's look at this problem. This was our example problem. Okay. We're looking at this limit. What type of indeterminate form is this?
0 over 0.
0 over 0. Because what's the natural log of 1?
0.
Everybody? Natural log of 1 is
0.
0. All right. So this has indeterminate form. 0 over 0. Please, folks, if you just wrote equals 0 over 0, erase it immediately. Okay. All I'm doing is identifying the indeterminate form. Okay. So does the Hopitals Rule apply?
Yes.
Yes. Let's try it. That doesn't mean it's the best way to go, but let's try it. Okay? So here we go. I'm going to apply the Hopitals Rule so that your reader knows what in the heck just happened, that you didn't do some crazy algebra step that they weren't aware of. Say that you're applying the Hopitals Rule. Okay? How do I apply the Hopitals Rule? Well, I'll take the derivative of the numerator over the derivative of the denominator. What's the derivative of my numerator? 1 over x. What's the derivative of the denominator? 1. Folks, this had indeterminate form 0 over 0 before we got started. This is no longer an indeterminate form. What's more, we can now apply the direct substitution property. Okay? So this is equal to 1 over 1 divided by 1, which is just 1. That was the easiest limit you ever evaluated. Okay? Next page. Let's look at this one. Does this have an indeterminate form? What's that? Bingo. Remember here what Caleb said? It's infinity over infinity here. It's our indeterminate form. Okay. So does the Hopitals Rule apply? Okay. I'll leave it to you to start learning when it is a good idea to apply it, just because it applies. Okay. I would argue that for my very first example, for this one right here, it was silly to apply the Hopitals Rule. You could have gotten there with algebra just as fast. Okay? But in this case, I couldn't get there with algebra. Okay? So let's go ahead and evaluate this limit. Well, we're going to apply the Hopitals Rule. So this will be now the limit as x approaches, it's still approaching infinity, of the derivative of the numerator. What's the derivative of the numerator? Okay. So this, in fact, I'm going to take an extra line. I'll write the derivative of the numerator over the derivative of the denominator. You don't have to do that, but it might just kind of help solidify what we're doing here, which is the limit as x approaches infinity of e to the x over 2x. Did we get anywhere?
No. Still infinity over
Yeah, I would argue that we didn't make the problem any easier, but we also didn't make it any harder. And some might argue that, hey, the denominator just got less complex. It was quadratic, now it's linear. This still has indeterminate form what?
infinity over infinity.
Still has indeterminate form infinity over infinity. Worked once. We didn't break it. Let's try it again. Let's again apply the Hopitals Rule. This gives us e to the x over what?
2.
2. Is this an indeterminate form?
Yes.
No.
No.
No. What's happening? The denominator's fixed at 2. What's the numerator doing? Getting arbitrarily large. What is this limit? The limit is infinity.
You can take it infinite, like you can keep on using that rule like pretty much infinite.
Yeah, well, the hope is to eventually get somewhere, right?
Yeah.
The hope is to eventually get somewhere. Here's an example where we did it twice. Okay, and then we got off the merry-go-round at the end of the second time. Okay? Now, there are some problems where you'll try to Hopitals Rule and you'll make it more complex. That you're probably doing it the wrong way. There may be a way to rewrite the problem, who knows? Or you may not want to use the Hopitals Rule at all. So again, it doesn't solve every single question. That's why you got to work enough examples. Okay? All right. Let's look at letter C here. Okay? And each one of these, by the way, has sort of a specific point. Okay? Does this have an indeterminate form?
Yes. Infinity over infinity.
Yeah, it's still indeterminate form, infinity over infinity. Okay? So let's apply the Hopitals Rule. We get 1 over x divided by 1/3 x to the minus 2/3. Folks, in my head, I converted that to the exponent x to the 1/3, and then I took its derivative. Okay? So I could write this, I'm going to rewrite this one more time just to talk about it. Normally I wouldn't do this, but I just want to make sure we can actually talk about it correctly. So let me rewrite this as 1 over x divided by 1 over 3x to the 2/3. Does this have an indeterminate form?
Yes.
Who am I missing when I'm asking the question, does this have an indeterminate form? If I'm missing you, let me know, because we can talk about it.
Yes. It's indeterminate.
Everyone see it? What indeterminate form is it?
0 over 0.
0 over 0, right? The numerator, and here I mean the big numerator, as x gets large, the big numerator tends towards 0. For the big denominator, as x gets large, this denominator tends towards 0. So this has indeterminate form 0 over 0. Now, does the Hopitals Rule apply still?
Yes.
Should I apply it?
No.
I think not. It was especially helpful to apply the Hopitals Rule to begin with because I had this natural log function and a polynomial function. Sorry, that's not correct. It's not a polynomial function, but it's a rational function. Okay, powers of x. Okay? But now everything's in terms of powers of x. Let's do some cleaning up first with algebra before we apply the Hopitals Rule again. By the way, if I applied the Hopitals Rule again, I would actually get on a merry-go-round that would never stop. This would become minus 1 over x squared. This would become, I'm not sure, but more complicated. So we've got some, it would just keep getting more and more complicated, and it would never come to a point where I could easily evaluate it through direct substitution. Okay? So there's sort of two decisions. Can I apply the Hopitals Rule? If I can, is it a good idea? And you have to ask that at each step of the way. Okay? So I'm going to actually just simplify this using algebra. So let's see here. This would be 1 over x times 3x to the 2/3 over 1 when I invert and multiply. Okay. So let's see, that's the limit as x approaches infinity of, let's see, that's, well, let's just say 3x to the 2/3 over x, which is equal to the limit as x approaches infinity of 3 over x to the 1/3. There's lots of ways you could write it, but let's write it that way. Okay, all I'm doing is properties of exponents, subtracting it where appropriate. Okay, any questions on that? Okay.
My directions.
Well, it's not really direct substitution, but we now go all the way back to section 2.2 where we said if we take a number divided by an arbitrarily large number, it tends towards 0. Okay, so it's not quite direct substitution property, but it was just an idea that we discussed. A number divided by something that's becoming arbitrarily large approaches 0. Yeah, Mike.
So basically what we're trying to do is we're trying to get either the top or the bottom to just become a reasonable number. It doesn't matter which one does.
Yeah, I mean it is problem dependent which one's going to simplify
I mean,
first.
the zero can't be on the bottom. I get that.
Right.
But, you're just trying to get it out of these two forms. Once it's out there, then you have a chance of.
I would almost say just potentially.
Yeah.
So again, it's an extremely powerful tool. It will take care of, in fact, if you were to go back and apply it to a lot of the challenging limit questions from before, because I remember I said this early on that almost all of our limit questions were of indeterminate form 0 over 0. I mean, almost all of them were from the first chapter. And so that means the Hopitals Rule might apply to almost all problems from the first chapter. Does it help you? I don't know. I wouldn't use it with a multiplying by the conjugate of a square root problem because taking derivatives of square roots gets messy. And doing the algebra is faster. But you could. Yeah. All right, let's look at this one. I can't remember why this one's in here. Let's find out. Oh, let you guys try it. Identify the indeterminate form if there is one. If it's appropriate, apply the Hopitals Rule. And give it a shot. What's that? I do. Yeah, I haven't taught it here before. We're on to it. So this has indeterminate form what? 0 over 0. Okay, so we apply the Hopitals Rule. Tell me that you're applying it. That gives us the limit as x approaches 0 of the secant squared of x minus 1 all over 3x squared. Is this an indeterminate form?
Yes.
Okay, I got a sneaking suspicion a lot of you don't know what the secant of 0 is. What's the secant of 0?
1.
It is 1. Right? And then you square it and you get 1. So what is this? This is indeterminate form what? 0 over 0. You do have to identify it. Because let's say there was just a secant squared here. Then it would be 1 over something tending towards 0, and it's not an indeterminate form, and you could not keep applying the Hopitals Rule. You'd have to use some other rationale to get through the problem. So you really ought to identify it each step of the way. Okay? So let's see, we'll take the derivative again. We get the limit as x approaches 0 of, let's see, that would be 2 secant x, because what's the derivative of something squared? It's 2 times that something. But then by the chain rule, secant x, tan x. Oh my goodness, Charles. What is this doing on here? Okay? We got to apply it one more time. I guess this is, so that's 2 rounds on the merry-go-round. We got to go a third time. Let's see, 3h, or LH would be the limit. What am I going to do here? I'm going to take the derivative of the numerator and the denominator again. Okay, so let's see here. That would be 4 secant x times secant x tan x tan x. I'm going to take this onto another page, folks. Camera, there it is. So that was so what I did, folks, is I wrote these two together. In fact, let me do it up here. So do it. All right. let me rewrite this as the limit as x approaches 0 of, I find it, rather than doing a triple product rule, it'll be easier to do it as a chain rule problem. Okay, so that's what I was doing there. So this through Hopitals Rule then would be the limit as x approaches 0 of, so I'm going to do the, in fact, let's just do the first. So 2 secant squared x times the derivative of the second, which will be another secant squared x, plus the second, which is tangent, times the derivative of the first, which will be a 4 secant x times secant x tan x, all over 6. Okay. We got there, right? This no longer has an indeterminate form, and we can evaluate through direct substitution. In this case, we don't get a very exciting answer. Our answer is 0, because of those tangent terms in each one. Oh, wait, no, that's a plus tangent.
Yeah.
Oh, no, we're good. We actually get something interesting. So this would be 2 times the secant, I'll go ahead and write it all out, secant squared of 0 times the secant squared of 0, plus, I didn't see that, so that's where I made the mistake, plus tangent of 0 times 4 secant 0, secant 0, tangent 0, but remember that the tangent of 0 is what? 0. But the secant of 0 is 1, so we get 2 times 1 times 1 plus 0 over 6, which gives us 3 over 6, which gives us a half. I find that just baffling, folks.
Wait, what? Isn't it 2 over? Oh,
Oh, sorry, which gives us 2 over 6, which gives us a third. Thank you, Caleb. Okay, which gives us a third. Folks, I find that incredibly baffling. I've still not wrapped my head around some of these complicated limit problems. The original problem, we'll jump back to it here once you get it copied down, was balanced in such a way, the numerator and the denominator was balanced in such a way that even though one was approaching 0, both were approaching 0, in the tug-of-war match, where did they meet? They met at 1/3. I find that just, and by the way, if it had been shifted off just slightly, it would either gone up to infinity or down to 0. But I think of it as like a perfectly balanced fraction that arrives somewhere. And I don't know, these still just, I don't know, they make me happy. This problem was just balanced in just the right way. That as the numerator approaches 0 and the denominator approaches 0, there's a tug of war, there's a competition. It's either going to arrive at infinity or at 0 or somewhere in between. And in this case, it arrived at 1/3. And I don't think there's anything in the original problem that would hint at that. I think these are really interesting. All right. Number E. Go ahead and do number E. Yeah, that's approaching pi from the left. What'd you say, Sawyer?
Should be in trunk. It should be 0 to 0. That's the form.
Is it? Slava, what do you say?
Cosine of pi is -1.
What's the cosine of pi? It's -1. So what's the denominator approaching? The denominator is approaching 2, I think, because it'd be 1 minus a minus 1, right? So this has the form, if you want, it's not an indeterminate form, it has the form 0 over 2. Specifically, what could you do right away with this problem? Apply direct substitution on it, right? So, in fact, Hopitals Rule doesn't apply. In a moment here, let's answer the question. In a moment, we'll apply Hopitals Rule and see that we get the wrong answer if we apply Hopitals Rule. It's not that, well, you didn't have to apply it. It would be wrong to apply it in this problem. Okay? So this can be evaluated through direct substitution. It will just be equal to the sine of pi over 1 minus the cosine of pi, which is equal to 0 over 1 minus a minus 1, which is equal to 0 over 2, which is equal to 0. Okay? I find this extremely beneficial to look at because if you tried to apply LHospitals Rule, so let me put this in big letters, this is wrong. The limit as x approaches pi from the left of the sine of x over 1 minus the cosine of x. If you went ahead and just carelessly applied the Hopitals Rule, which you could, in theory, I mean, you could do the action, right? You're not allowed to apply it, but you could do the action. You'd get the limit as x approaches pi over pi from the left of, let's see, that'd be the cosine of x all over the sine of x. In which case, this no longer has indeterminate form, which it never did to begin with. This is the Hopitals Rule. Again, I'm incorrectly doing this. And you would say, okay, the numerator is approaching a fixed positive number, in this case, or negative number, -1, and the denominator is approaching 0. We're approaching it, though, from which way? Well, we're approaching pi, so we're diving down towards it from the left, so it's positive. So this would be -infinity. And you'd be absolutely dead wrong in your answer if you applied the Hopitals Rule, where it does not apply. It has to be an indeterminate form, 0 over 0. Okay, next page. All right, so the rest of this is how do we apply the Hopitals Rule to some other indeterminate forms? Okay, sometimes I'll do a couple of examples, sometimes I'll just do one, but I always give you the steps. Suppose you have the indeterminate form 0 times infinity. Okay? Again, the way you kind of talk yourself through that, right? One expression's approaching 0, and usually 0 times anything is 0. But the other expression's approaching an arbitrarily large number, and something times an arbitrarily large number stays arbitrarily large. So you've got these kind of two competing ideas here. It is an indeterminate form. Okay? Well, the way you should do it is rewrite it as a quotient. Either rewrite it as f over 1 over g, or g over 1 over f. That will either put it into the form 0 over 0, or infinity over infinity. So let's look at the example here. Okay? And I don't remember which is the right way, but we'll give it a shot. We've got the limit as x approaches 0 from the right of x ln of x. What is the indeterminate form here?
Infinity times 0.
Yeah, so it's 0 times, careful, -infinity is the indeterminate form here. Does everyone see that? What's x approaching? 0. What's the natural log of x approaching? Well, we're approaching 0, but from the right. And what does your ln curve look like? Looks like this. So as I approach 0 from the right, what are my y values doing? They're becoming arbitrarily large negative, or arbitrarily negative. Okay? So what does my little rule up here say to do? It says to try rewriting it as a quotient. Okay? So I think what I'd like to do is to rewrite the problem this way. I'm going to go ahead and take this natural log below the line. Okay? Folks, if you went the other way, if you brought the, that's not quite true. I have to write it as 1 over the natural log of x. I'm a liar. That would work. I want to do it this way. So I want to do the natural log of x over 1 over x. Is that a legal move?
Yes.
I brought this x down below the line, but I also inverted it. So we're fine. I could have done it the other way. It would be a little bit harder if I did it the other way, because I'd have to do a quotient rule on 1 over ln x, which is a little bit hard to do. Okay? So I chose to do it this way. Okay. So now what indeterminate form does this have? This has indeterminate form minus infinity over infinity. Does everyone see that? So now let's go ahead and, oh, he's my hero. Say his name right. The Hopitals Rule. Yeah. He's not my hero. I don't know anything about him. So what's the derivative of the natural log of x? It's 1 over x. What's the derivative of 1 over x? It's minus 1 over x squared. Okay. This still has indeterminate form, infinity over infinity, I believe. Or infinity over minus infinity. It still has an indeterminate form, right? So we could keep going with the Hopitals Rule. Should we?
No.
Yeah, my gut says no. We're down to polynomials. Let's just see what we can do to clean this thing up. So if we go ahead and invert and multiply, we would get negative x squared over x, which is equal to the limit as x approaches 0 from the right of negative x, which is equal to 0 through direct substitution. What's that?
No, it's pretty cool that we can use multiple rules.
I think it's an extremely useful tool. Okay. All right, so I'm only doing one example of this. You'll have 3 or 4 in your homework. What's the idea? If it has an indeterminate form, 0 times infinity, you take one of the factors below the line and invert it. Okay? Sometimes there's a right choice. Folks, if you take a factor below the line and invert it, you get an indeterminate form, but when you apply the Hopitals Rule, you get something far more complicated than what you started with. Switch it and try taking the other one down below the line and see if that helps. Okay? Okay. Let's look at this one here. If you have indeterminate form infinity minus infinity or vice versa, you have to go ahead and get it into a quotient. How are you going to do that? Well, you're going to have to introduce a common denominator or by factoring out some sort of common factor. Okay? So let's see here. For this particular problem, because we're in terms of secant and tangent, and 1, I have a hard time with working with those, and 2, because my clue is to try to write as a fraction, and trig functions are always fractions of some sort. Let's go ahead and put this into terms of sine and cosine. So this would be 1 over the cosine of x. Oh, by the way, I didn't identify it. What is this indeterminate form? Okay. From the left, pi over 2 from the left. Yes, so this would be infinity minus infinity. Good. So this is indeterminate form, infinity minus infinity. By the way, if it was of the form infinity plus infinity, could you go ahead and evaluate that?
Yes.
Yeah. What's an arbitrarily large number plus an arbitrarily large number? So, folks, I used to think I knew what I was doing with infinities, this concept, this idea of infinity. Then I got really scared of it. And then I learned where I had to be careful and where I don't have to be careful. It's the indeterminate forms that you have to be careful about. Okay? That's where you cannot use any sort of reasoning, because your reasoning will be wrong. Okay? All right. So what I'm saying is if this had been a plus sign, you could have stopped right there and called the answer infinity. It's arbitrarily large plus an arbitrarily large, which isn't an indeterminate form. Minus the sine of x over the cosine of x. This is all ready to go. It almost came prepackaged to write as a fraction, right? So this gives us the limit as x approaches pi over 2 from the left of 1 minus the sine of x over the cosine of x. Did I make my problem any easier? No. But what? It now has indeterminate form 0 over 0. Do we see that? What's the sign of 0? Sine.
Pi over 2.
Oh.
Sine of pi over 2.
Well, sorry, thank you. What's the sine of pi over 2? Thank you. What's the sine of pi over 2? 1. So we get 1 minus 0. Good. And what's the cosine of pi over 2? 0. So this has indeterminate form 0 over 0. That one's broken. Okay. We apply the Hopitals Rule. Okay. that gives me minus the cosine of x all over the
Negative sign.
minus sine of x, which gives me the limit as x approaches pi. There's lots of ways I could argue through it. I'm going to go ahead and rewrite this as cotan. And we get 0. So what's the takeaway? I mean, it's had kind of an interesting result. What's the takeaway from this example? If you have this particular indeterminate form, you come up with a creative way to write it as a fraction. Then it will either have, well, it should have indeterminate form infinity over infinity. Okay, so I just want to reiterate what the Hopitals Rule says. First of all, it says if you have a certain type of indeterminate form, then rather than taking the limit of the ratio of two functions that form one of those indeterminate forms, you can take the limit of the ratio of those two functions' rate of change, meaning their derivatives. Okay. What are the two indeterminate forms for which the Hopitals Rule applies? 0, 0, and yeah, plus minus infinity over plus minus infinity, which I'll usually just from here on out say infinity over infinity. It's any combination of those pluses and minuses. Okay. Those are the two situations for which the Hopitals Rule immediately applies. Okay. So let's jump back. So I'm only doing one example of each of these. In their homework, you'll get to try 2 or 3 examples of each one. Okay. This last one is these indeterminate powers, which are probably the most time-intensive and kind of, I don't know, they're the most complicated of them, I guess. You've got to sort of bring together all the tools we've just been talking about, plus some others. So when you have an indeterminate power, like 0 to the 0, infinity to the 0, or 1 to the infinity, those are all considered indeterminate forms. They fail your logic. They fail your traditional kind of experience with numbers. So anyway, let's look at this one here. Let's identify its indeterminate form. Careful, sine of 0 is 0, so this is going to be a 1, 2, and then what is, as we approach 0 from the right, what's our cotangent approaching? It's approaching infinity, right? Folks, your cotangent curve, it's got asymptotes. It's got asymptotes here, 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 and your cotangent curve looks something like this. So as we approach 0 from the right, we're approaching positive infinity. Okay. So this has the indeterminate form 1 to the infinity power. All right. I actually promised to do this one for you way back when we started that indeterminate forms handout. Okay. Let's see what happens here. So the trick is to go ahead and rewrite the original indeterminate power as e to the natural log of that indeterminate power. So let's do so. This is equal to the limit as x approaches 0 from the right of e to the natural log of 1 plus the sine of x all to the cotangent of x. Why is that true? Because e to the natural log of an expression is just that expression, as long as that expression was initially positive. Now, I'm going to do 2 steps at once, folks, just to save me writing. The first step is we said that limits can pass inside continuous functions, and e to the x is about as continuous as they come. So I can pass this limit inside e to the x. So I'm going to write it as e to the limit as x approaches 0 from the right of, and then I'm going to do one more step. But does everyone understand what I just did? I passed the limit inside the continuous function. Okay. Then, here I've got the natural log of an exponent, and we said we could pull powers away from exponents outside the natural logs as factors, right? So this becomes the cotangent of x times the natural log of 1 plus the sine of x. So I did 2 steps at once there. Passed the limit through the continuous function, and then did that log property. And that log property should seem familiar. In fact, if you're following my math lab's way, sometimes my math lab had you do your logarithmic differentiation problems like this. It should seem a little familiar, putting e to the natural log. I didn't have you do it then in that section. Okay. So
This now has indeterminate form what? Sorry, I'm pointing at the entire expression. This now has indeterminate form what? Well, this is still approaching infinity, right? Infinity times, now what's 1 plus the sine of x? That's approaching, so approaching 0, that's approaching 1, and then the natural log of 1 then would be 0. So this has indeterminate form, excuse me, infinity times 0. What do I do now? Rewrite it. What do you mean, Tasha?
Rewrite it as a fraction.
Yeah, so right now it's an indeterminate product, and the Hopitals Rule only applies to indeterminate quotients. Let me give myself a little room here. So we can rewrite that as e to the limit as x approaches 0 from the right of, which one should I take below the line? Which one do you think is going to be easiest to take below the line, invert, and then take the derivative of?
Cotangent.
Yeah. Specifically, we saw before, it did not work out nicely to take log below the line. So let's leave it upstairs. We get the natural log of 1 plus the sine of x all over the tangent of x. And this now has indeterminate form what? Well, this is approaching 0 in the numerator, and the tangent as x approaches 0 also approaches 0. So at long, long last, we're ready to apply LHospitals Rule. Okay, we use LHospitals Rule for 0 over 0, infinity over infinity, but for most of the other indeterminate forms, through some clever algebra, we can rearrange it so we can still use LHospitals Rule. And that's what we've finally done. So now we'll apply LHospitals Rule. This gives us e to the limit as x approaches 0 to the right. So notice this e to the limit part is just kind of tagging along for right now. Here I apply LHospitals Rule. Okay, taking the derivative of the numerator, that's 1 over 1 plus the sine of x times the cosine of x by the chain rule, all divided by the secant squared of x. Cassidy.
When you apply the Hopitals Rule, do you apply it to the entire function or only the function inside the limit?
Yeah, so the Hopitals Rule is a statement about limits. So it says that the limit of the ratio of these two functions, if it's one of these two indeterminate forms, will be equivalent to the limit of the ratio of these two functions. So yeah, it's happening only inside the limit. Yeah.
Where do you go from cotangent to tangent?
Yeah, so remember what we said to do. So this was indeterminate product, infinity times 0, so we had to write it as an indeterminate quotient. So we wanted to so we brought it down below the line, but then we also had to do what? Yeah, invert it. So brought it below the line and inverted it. Okay. Are we out of the woods? I think we are. Let's just do one more line to clean it up. That's e to the limit as x approaches 0 from the right. Actually, it's not really going to clean it up much. Maybe it wasn't worth writing. Cosine x over 1 plus sine x, all divided by secant squared x. Okay. Is this an indeterminate form? What's the secant of 0? Secant of 0 is what, folks? 1. So that's fine. Sine of 0 is 0. Uh-oh, but I add it to 1, so that denominator is fine. I think we're okay. So what do we end up with? We end up with e to the limit. As well, in fact, we're evaluating this through direct substitution, so we end up with e all to the 1 over 1 plus 0 all divided by 1, which cleans up to be just e to the 1, which equals e. Da, 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 da. What on earth? Let's think about, I mean, that should, I find that a little bit surprising. Somewhere you learned a fact, so this was 1 to the infinity power. Somewhere you learned a fact that 1 times itself is always what? 1 times itself a certain number of times is always 1. Okay. But if we take a number, notice this is we're approaching 1 from the right, or approaching 0 from the right, which makes this number always just a little bit bigger than 1. So any number that's just a little bit bigger than 1 raised to a power is going to keep growing. So you've got this competition, this tug-of-war match. And lo and behold, in this tug-of-war match of something wanting to go off to infinity and stay put at 1, it ended up where? At e. These are really interesting problems. Hopefully that gives you some insight into these indeterminate forms and how we can use derivatives to evaluate them. Any questions on that? All right, so for fun, everyone do 13a. Let's take a couple. Folks, if you made a mistake on that, that's not the end of the world, right? You dropped a negative sign somewhere or something like that. Okay? Do work through this. I think these are kind of fun. Okay? If you're looking for something to do on a Friday night, try to write one of these. Try to come up with one where you take the Hopitals rule and it keeps applying and applying, applying, and applying, and then finally you get off the merry-go-round. They're kind of fun to come up with. I used to build them from scratch. Now I found a faster way to do it. So, by the way, in fact, the relationship between cosine and these particular polynomial functions is something that you'll learn in Calc 2. Okay? All right. That's all I want to do with the Hopitals rule.